Okay, guys, let's review the last part on stopping times and Wald's identity. So stopping time is a random variable that is, it can be a random variable or a defective random variable, which means that it can actually take the value positive infinity with a positive probability. So it is a random variable or a defective random variable. Some people call it extended random variable. That is associated with a sequence of random variables. Okay, so it does not exist. It does not exist like on its own. And so suppose that we have a sequence of random variables x1, x2, and so on, and v is a stopping time with respect to this sequence of random variables. If one of the sequence, one of the events, and you can choose which one depending on the situation. So that v is equal to tau, or v less than or equal to tau, or v greater than tau. So you can study any one of these. And if you discover that the event depends only on x1, x2 up to x tau, and it does not depend on any other x, then in that case we say that v is a stopping time. Here the indexing is from 1. You can start from 0 as we will do in Markov chains. And as I said, that v can be a defective random variable, which means that it can take the value plus infinity. So n of t plus 1 is a stopping time with respect to the inter-arrival times. So in renewal processes, what is the sequence? You can think that our sequence is the sequence of inter-arrival times, u1, u2, u3, and so on. And so those guys are IID. And nt plus 1 is a stopping sequence, is a stopping time. Why is this? Because if you want to investigate nt plus 1 is equal to m, okay, so we want to investigate this event. So n of t plus 1 is, so if you investigate this guy, n of t plus 1 is a stopping time if, and only, so it's by definition, if it depends only on the random variables x1, x2 up to xm. That's it, and is independent of the others. So xm plus 1, xm plus 2, and so forth. Okay, so that's basically the idea. So is that true? So in our case here, it means that can you study basically the event n of t plus 1 is equal to m? Can you study it just by knowing the inter-arrival times u1, u2 up to um? And the answer is yes. Basically, this event is true. N of t plus 1 is equal to m. N of t plus 1 is equal to m. It exactly means that n of t is equal to m minus 1, which means that if you inspect the system at time instant t, there should be m minus 1 arrivals. M minus, so it means that arrival m, it happens after the time t, okay? And basically arrival m minus 1, it happens at t or less. So basically this event can be studied by examining this inequality. This event is true. N of t is exactly equal to m minus 1 if t is greater than or equal to this sum. So remember that this sum is the time of occurrence of event m minus 1, and this is strictly less than this sum, which is tm. If that is the case, then n of t plus 1 is m, or n of t is equal to m minus 1. Now, if t is somewhere else, is not between these guys, then basically this event is false. It's not true. Note that basically you can decide about this event. You can know whether it's true or false completely without any uncertainty by knowing the inter-arrival times u1, u2 up to um. You don't really need at all something like um plus 1 or um plus 2 or anything. Give me u1, u2 up to um, and I can tell you exactly whether n of t is equal to m minus 1 or not. So basically n of t plus 1 is indeed a stopping time with respect to the inter-arrival sequence of random variables. N of t itself is not a stopping time, because n of t itself is not stopping time, because if you study n of t is equal to m, okay, then basically this requires, so is this true? You want, if n of t is equal to m, is the number of arrivals at time t is equal to m, this requires knowledge of u1, u2, up to um and un plus 1. You need to know this guy. You need to know this guy. Why? Okay, why do you need to know um plus 1? Right, so you know the time of the nth arrival, right? So you know basically those guys, and so you know tm, you know the time of the nth arrival. So you know those guys, but does this mean that n of t is equal to m? Perhaps there is an extra arrival between the sum. So right, so here basically between u1 up to um, okay, so there is this time, so this is a time, and then there is the time t. Okay, so this is basically t of m, which is the sum. Now, is n of t is equal to m? We need to know um plus 1, because if um plus 1 is here, then basically this means that n of t is actually greater than m, and if um plus 1 is here, then n of t is equal to m. So you need, the story is that you need u of m plus 1. You cannot without any uncertainty make sure of this event that n of t is equal to m without knowing this guy. So according to the definition of a stopping time, if you study the event that the random variable is equal to m, the random variable is a stopping time so long as it depends on the elements of the sequence up to, in our case here, um. But here we need um plus 1 to make sure that actually whether n of t is equal to m or not. So n of t itself is not a stopping time, but n of t plus 1 is a stopping time. Okay. So Wald's identity is about this. What if you have a summation of random variables, and then you have the number of terms in the sum is a stopping time with respect to the sequence that you are summing? So according to Wald's identity, basically the expectation of this summation is equal to the expectation of one of those guys. So those guys are IID, random variables. Okay, and like with finite first moment, and so this is actually the situation that we have here. We have the inter-arrivals are IID by definition. No renewal process, cannot satisfy this. By definition, the arrivals must be IID. And then moreover, at least in this part, we are also assuming that the first moment of the inter-arrival time is finite. So in that case, this expectation is equal to the expectation of x1. Okay, in our case will be the expectation of u1, and multiplied by the expectation of this stopping time. Okay, and let me just do this for a positive x. It's just one line for positive x's. So what is this expectation? Well, this expectation, rather than having a summation from 1 to v, what we can write is have a summation from 1 to infinity, so summation over the natural numbers or the positive integers, and then we have an indicator, and this indicator is for v greater than or equal to g, right? So this means that your sum, the summation index is less than or equal to v, because the original sum here, you stop at v. So you can basically go to infinity and have the indicator that j is less than or equal to v. Now, if your random variables are non-negative, then basically you can interchange the order by Tonelli, and then you will get this expectation. So what is the expectation? So the expectation is expectation of xj and of v greater than or equal to j. Now v is an integer valued random variable. So basically this is exactly equivalent to expectation xj, indicator v strictly greater than j minus j minus 1. Okay, so we are saying that v is a stopping time. So v is a stopping time. It means that this event here, because v is a stopping time, so with respect to x1, x2, and so on, then the event v greater than j minus 1 is independent of x of j plus 1, x of j plus 2, and so forth. Okay, so basically these two guys will be independent of one another. Here we have x of j, so expectation of a product is product of expectations, and basically this is what you get, the result here. Okay, and like here is the argument, you know, how to do it if basically the x's are positive or negative. In our case here, you know, it's you know, I mean, you can read the general case, but like our random variables specifically here, and I think also in when we study Markov chains, it will happen that, you know, our guys are non-negative, but you know, you can, it's a general result. And this is like a very important example. Basically, let's use this Wald's identity to obtain the mean value of Tn plus 1, T sub n of t plus 1. Okay, T sub n of t plus 1. Remember that we have this inequality. I mean, you know, we will actually use it today also, that basically t is greater than Tn of t is strictly less than Tn of t plus 1. Remember this inequality, which again may seem like complicated, but you know, just assign a value to n of t, any value of your choice, and you'll find that this inequality is true. Like if n of t is 5, this means that t5 is less than or equal to t less than or equal to t6. Okay, so here if n of t, if I set it equal to 5, which makes sense. If the number of arrivals at instant t is equal to 5, then the fifth arrival occurred at a time, you know, from 0 up to t, and then it must be the case that the sixth arrival or the next arrival, it happens after t, right? And remember that basically the residual time was this guy, n of t plus 1 minus t. This difference here is the so-called r of t, which is the residual time. Okay, and so basically, if I compute this expectation, I can, you know, so basically if you know this, the expectation of the residual time is the expectation of this quantity here, okay, minus t. I can just subtract t and there you go. So without doing the derivation of the previous lecture. So the previous lecture, basically we obtained the PDF of the residual time, and it's not a nice PDF at all, right? So the moral of the story is actually you can obtain the first moment of the residual time easily using Wald's identity. You do not really need like to go and compute the full PDF and then or the CDF or complementary CDF and then use them to obtain the first moment. You can just compute the first moment directly, and here's the way to go. We need to compute the first moment of this guy. Okay, so what is this guy? The occurrence of event n of t plus 1. Well, it is a sum of interarrival times from 1 to this index here, which is n of t plus 1. Okay, the challenge here is that the upper limit of the summation is itself a random variable. Oh, but it is the random variable n of t plus 1. It's not any random variable. It's the random variable n of t plus 1. And this is an IID sequence. So those guys are IID because this is how we define renewal processes. And the number of terms in the limit is indeed a random variable, but it is this special case of random variables called stopping times. It's a stopping time with respect to the sequence u1, u2, and so on. Why? I mean, this basically is the example here, that the random variable n of t itself is not stopping time, but n of t plus 1 is a stopping time. So we can apply Wald's identity, which simply tells you, you know, basically the expected value of this thing is, you take the expected value of the interarrival time, and then you take the expected value of this random variable. And, you know, by definition, expected of n of t is equal to m of t. And if you take this thing and subtract t, then you actually get the expected value of the residual time. So Walt's identity can be very useful, like again, in doing something like this without worrying about what is the BDF of the residual time or anything. Note this, it's extremely important. Now, suppose that you are playing this game with something in which the upper limit here is n of t. You cannot use Walt's identity. You cannot use Wald's identity because n of t is not a stopping time with respect to the inter-arrival sequence. N of t plus 1 is a stopping time. N of t itself is not a stopping time. And of course, you know, this Wald's identity is general for any stopping time. You know, stopping times will be used again when we talk about Markov chains. Okay? Any question? Okay, so the elementary renewal theorem is basically, so last time we showed that basically n of t over t as limit t goes to infinity, that this is 1 over the expected value of u. Now we want to do the same thing, but with n of t replaced by its first moment, which is n of t. Okay, and this is called the elementary renewal theorem. Okay, so first idea is this. So we will use basically t less than n of t plus 1. Less than or equal to t, so this t n of t, so this again, it's very important in renewal processes, and is specifically we will focus on this part here. We will focus on this part. Okay, so you start with this one, and you simply take expectation of both sides. So if you take the expectation of t, well, t is just the time instant, it's a constant, and so it is t, and then the expectation of t n of t plus 1 is this thing that we computed using Wald's identity as expectation of u n of t plus 1. Okay, then rearrange the terms so that you get n of t plus 1 over t is greater than 1 over expected value of u. Now, let's, you know, again, like we did so many things here in a non-rigorous way. Let's try to be rigorous again, at least, you know, for this part. And, you know, let's just assume that we don't really know whether this limit exists or not. Okay, so we will compute limit infimum rather than limit. I will take limit infimum, and so basically limit infimum of m of t over t plus 1 over t as t goes to infinity. Well, you know, this limit is the sum of the limit infimum typically and limit supremum. They do not apply, they do not basically, you know, they do not, obey things that, you know, the limit of the sum of limits. However, if one of the terms has a conventional limit, you know, that is well defined, then you can actually apply the sum rule. So basically, limit infimum of this summation here, it is because limit of 1 over t as t goes to infinity is equal to 0, so it is defined, then limit infimum of this summation is indeed limit infimum of this guy plus limit infimum of that guy, and the limit infimum is equal to the limit is equal to 0. Okay, so you take limit infimum, this will give you limit infimum of t over t. For now, we cannot say whether the limit exists or not. And then on the other side, we do not have any dependence on t, and so the limit infimum will be this quantity here. And whenever you take the limit of both sides of an inequality, you know, you need to change the, you know, you need to change the strict inequality into an inequality with a possibility of equality. Okay, so that's you know, sort of a bound. So you can see where we are going. Like, you know, the idea, if we can, you know, limit infimum. Okay, so you know, if you are basically doing this proof from scratch, then if you start from here, then you say, okay, so here's the plan. Limit infimum is always less than or equal to limit supremum, right? Is equal to, always limit supremum m of t over t, right? And now, if I show that limit supremum m of t over t, if this guy is less than or equal to expectation of u, which is the guy here, then everything is equal. Then everything is equal, and the limit exists, and is what is given in the elementary renewal theorem. Okay, so again, so it's a bounding game. So you take limit, you say limit infimum is greater than or equal to something, then from analysis, limit infimum is always less than or equal to limit supremum, and then if you show that limit supremum is less than or equal to the same limit, which is a lower bound on limit infimum, then basically everything is equal. Now, showing that actually getting this upper bound is a bit tricky, okay, and here is the trick, you know, that is used. So again, it's not like a straightforward trick. So the trick here is to construct another renewal process. To construct another renewal process in which the inter-arrival time is bounded. Okay, so here is again, it's not something that that will come to you like just like this. Okay, so it's definitely a trick that requires like several trials till you basically get it. So we will define a process here. I will basically denote its parameters by tilde. So u tilde is u if u is less than or equal to m, which means that so basically you have the original process. Okay, so the original process, so this is 0. This is the time axis, where time can be actually not time. It can be any other coordinate, even an abstract variable, but we typically refer to it as time. Then you have those guys. So this is u1, this is u2. Let's say that this is u3, this is u4. Those are the inter-arrival times. So what you do is the following. You specify big M. You specify big M, which is a positive number. And now, if u is less than or equal to big M, you keep it as is. So basically, here let's assume that M is greater than those guys. So basically, u1 will be u1 tilde, okay, because u1. So suppose here that u1 is less than M, and u2 is even smaller, and so this will be u2 tilde. Up till now, so basically u1 is less than or equal to M, u2 is less than or equal to M. Let's suppose that M is actually less than u3. So suppose that M is less than u3, then in that case, so this is u3 in the original process, and suppose that u3, I assume that it is greater than M, then in your new process, you will truncate the value at M. So basically here, you will have, this will be u3, so this will be M, and it will be u3 tilde. Okay, and then this is the same thing, u4 is right, so you have here u4 tilde equal to u4. Okay, and so on. So what you do is the following, like you have this sequence of inter-arrival times. Think about it like this. Again, it's like you go and visit each inter-arrival time. If it's less than or equal to M, you keep it as is. And if it exceeds M, you simply replace this inter-arrival time by M. Okay, so again, like you are bounding here, you do not allow you to basically take arbitrarily large values. And so you start getting something that looks like this. Okay. So, okay, let's basically study. So the idea is that here we have an inequality that looks like this. Okay, so you want sort of another inequality like in the other direction, and the problem is that if you allow if the inter-arrival time is a random variable that can take arbitrarily large values, then you will have a problem in having an inequality in the other direction. So see, the trick here is like t less than something. So you want t to be greater than something. You want t to be, so you get it by doing this trick. Right? So now t tilde of n tilde t plus 1 is less than or equal to t plus m. So this is tilde, this is for the new process. Why? Remember what is basically, so t tilde n of t plus 1 minus t, okay, is the residual time. Is the residual time in basically in the new process. Okay, and now because the inter-arrival times cannot exceed m, then if you inspect the process at any time t, then the next arrival will happen. It will happen somewhere before m seconds elapse. Okay, so that's basically the idea. The idea is to use this modified renewal process with a bound on the value of the inter-arrival time, so that you can upper bound basically this quantity. Of course, the cost of doing something like this is that by the end of the day you want to make a statement regarding the original process. Okay, so that's it's not like an easy thing to do. Like again, like you now have this inequality, and if you have this inequality, you will take the expectation of both sides. Okay, and then you can say that I will, for every m, for every t, I can choose m to be related to t somehow. I mean, I can choose m to be square root t or something like this. And you can basically show this inequality. Okay, so m tilde of t is less than or equal to this quantity. Again, the problem is, so here when we choose m to be square root t, the problem here is that, you know, it's a statement regarding the new process. Okay, it's a statement regarding the new process, while we want basically a statement regarding the original process. So here's the trick. The claim is that for any time t, m tilde of t is always greater than or equal to n of t, and m tilde of t is greater than or equal to m of t. Okay, and this comes from that. I mean, if you accept this, you just take the expectation of both sides, and you will get that. So why is this true? Why is this guy true? You know, at any time t, the number of arrivals in the new system is always greater than or equal to the old system. The reason is, you know, basically the inter-arrival times in both systems are the same, so long as they are less than or equal to m. If the inter-arrival time in the main process exceeds m, then you make it equal to m in the new process, right? So if we look at our diagram here, right? So suppose that you study this time instant. So suppose that you study this time instant, okay? This time instant. So at this time instant, n of t is equal to 1. So one arrival occurred here, and n tilde of t is also equal to 1, which is one arrival there, right? Okay, so suppose that you study another time instant. Suppose you study at this time instant. Okay, then n of t is equal to 2, n tilde of t is equal to 2. But now suppose that you study this time instant. Now here what we have is that n of the third arrival in the main process has not occurred yet. So here n of t is equal to 2, but from here actually n tilde of t is equal to 3. Now we have 3 arrivals, 1 and 2 and 3. So again, it's because you are shrinking. So u in the old process is kept as is if it is less than or equal to m. If it exceeds m, you sort of truncate it. And so this will make that at any finite time t, n tilde of t is greater than n of t. Take expectations of both sides. And so n of t is upper bounded by this guy. Okay, so that's the nice thing is that basically now you can, you know, the inequality that is established for the new renewal process, now, you know, it's sort of, we can, at least for the left-hand side, the left-hand side can be replaced by m of t over t. It's less than or equal to this guy, and it is less than or equal to that guy. We still have a tiny problem, which is that this quantity here, it's not expectation of u, it is expectation of u tilde. Okay, so it's the mean inter-arrival time, but for the modified process, not for the original process. Okay. Okay, so so again, you take limit supremum. Don't forget our original plan. Our original plan is actually to have limit supremum less than or equal to this quantity, so that we have everything is equal. So you take limit supremum as t goes to infinity, and the idea is that there is a term which is 1 over square root t. This will go to 0, and then you know, the remaining part of the proof is to show that actually this guy, as t becomes very, very, very large, this guy will actually converge to the expected value of u itself. Okay, and how to show this? So what is the expected value of u tilde? So long as the inter-arrival is between 0 to m. Sorry, remember what is u tilde? So u tilde is, I can write it like this. So u tilde is u indicator, it's u indicator u less than or equal to m, right? Plus m indicator u greater than m. Right? You can write u tilde as like this. It's like if u is less than or equal to m, then it's u. Then if u is greater than m, then it is m. So basically, u tilde is a function of u. So you can apply Lotus, the law of the unconscious statistician. So basically, the expected value of this function of random variable u is simply that you take it and insert it, you know, you multiply it by the PDF of u, and then you integrate, right? So you take basic integration from 0 to infinity u indicator u less than or equal to big M plus big M indicator u greater than or equal to M, and then you multiply by f of alpha, and this is fu, and then you split these two integrals. So one of them will be an integration from 0 to M, the other one will be an integral from M to infinity, and then the other integral, basically we are having this constant M, okay? So this is basically Lotus. So here we are doing Lotus, and now, so this is basically leave the first part. For the second part, what is the second part here? The second part is that M multiplied by 1 minus the CDF. And I think it was a homework problem or something like that, that basically you showed that if first moment is finite, this converges to 0 as M goes to infinity. Okay, so basically we took M to be square root t. If you take limit as t goes to infinity, M also grows without bound. And for random variables, if you take this M multiplied by the complementary CDF, so long as the first moment is finite, basically you can show that this will go to 0. And at the same time, as you take the limit as M goes to infinity, this other guy here will go to infinity, and you will get the limit M tends to infinity of integral 0 to M, 0 to infinity, actually 0 to M, okay, so 0 to M of alpha fu of alpha. But by definition, this is basically integral from 0 to infinity, alpha fu of alpha d alpha, which is the expectation of u itself. Okay, so nice trick. So the nice trick here again is like to have this intermediate process in which sort of thing. The idea is, so the one or the group thinking about this proof again is like, we want to do something like, we want something like, so here t is less than something related to the use, we want the opposite inequality. How can we have the opposite inequality? The inter-arrival time can be arbitrarily large. So that's the idea, is to truncate it and to apply this inequality, and then basically to fix things by showing that actually you can make a statement regarding the original process. And one thing here is that the modified process will always satisfy this inequality. So this is always true for any finite time instant t n tilde of t is greater than or equal to n of t. Okay, and so we are done. So you take limit supremum. Again, as I said, that. I am writing it here in a different way. So limit supremum is less than this guy, but from above this is less than or equal to limit infimum, which is less than or equal to limit supremum. Okay, and so once you have this chain of inequalities and these two guys are the same, then it not basically everything is the same, and so limit lim inf t goes to infinity, m of t over t is equal to lim sub t goes to infinity, m of t dt. And then we have the rule from analysis that if the limit infimum is equal to the limit supremum, then actually the limit exists. Okay, and what is the limit here? It's basically this guy, which is 1 over expectation of u. Okay, so this is the elementary renewal theorem. Any questions? Okay. So in some cases, we basically get like integral equations that can be solved by using the renewal function, and here the solution will involve the Laplace transform, and again you can just, if you need that, you want to take the Laplace transform, just use it, and the idea is that you have basically this integral equation. So we have g of t, so this is unknown, we don't know this guy, is equal to h of t, this is known, we know this guy, so this it's a known function of t. Plus g of t, again, okay, so this is unknown, we don't know it, and it is convolved with basically, the PDF of the inter-arrival times, or the PDF of, of a non-negative random variable, okay, and so this is known. So that's an integral equation, because if everything on the right is known, then it's sort of, we know what g of t is. But the problem is that g of t is here and it is there, and it's an integral equation because of course the convolution is this integration here. So we don't know this guy, which is also involved inside the integral. Okay, and then we know, I mean, you know this from from previous life, it's one of the motivations for the Laplace transform and Fourier analysis is basically to take a differential integral equation and basically turn it into an algebraic equation. So this is basically the trick. So g of t, it's Laplace transform of g of s, h of t, h of s, convolution becomes a product, g of t is g of s, and then basically the Laplace transform of fu is phi u. And then what you do is basically you have algebra now. You basically take this guy and move it to the other side. So 1 minus phi u of s multiplied by g of s is equal to h of s. And so g of s is equal to h of s over 1 minus phi. So basically you, in the Laplace domain, very easily, you separated g on one side and the known functions on the other side. Then again, if you choose the real part of s to be greater than 0, then the magnitude of this thing is less than 1. You can write down this series, and so you basically take 1 minus phi to 1 plus phi squared plus, and then you split this into two parts. So this is h of s multiplied by 1, okay, plus, and then you have h of s, and then you have phi of s plus phi squared of s plus again, okay, so you just like split, and then you can take phi u of s as a common factor, phi u of s as a common factor, so phi u of s, and so here we have 1 plus phi u of s plus phi squared and so on, and then this series you put it back as what, as phi u of s over 1 minus phi u of s, okay, and the reason of doing this is we want to basically match the Laplace transform of the renewal function, m of s. Okay, so that's basically the idea, that m of s divided by m of s divided or this thing divided by s is equal to m of s, and so basically this guy is equal to s m of s. Okay, and so now we have take the inverse Laplace transform. So the inverse Laplace transform, g of s becomes g of t, h of s h of t, and now we have a convolution. Now we have a product between these two guys. Now it will be a convolution. So this will be h of t, which is the time domain version of h of s, and then we have a convolution, and this is basically in the time domain. It's the first derivative of the renewal function. Okay, and so now so if you have an integral equation that looks like this, g of t is equal to h of t plus g of t convolved with the this PDF of the non-negative random variable u, then you can solve the integral equation using Laplace transform technique, and basically g of t now can be expressed in terms of h of t, which is this known function, plus h of t itself convolved with basically the first derivative of the renewal function, the dm of t by dt, where we know that basically, remember that the m of t itself is a complicated thing related to the CDFs like this. Okay, so it's a very complicated thing, but and you see, I think in the homework, like you will start like playing with this and obtaining m of t and so on. Okay, so is this useful? Let's actually use it in something related to renewal processes themselves. Okay, so that like sort of a direct application. Let's try to compute the second moment of a renewal process. Okay, so m of t is the first moment. So perhaps you are interested in the second moment. And remember, we did a proof in which basically all moments are finite for a renewal process if you assume that u is positive with probability 1. Okay, how can we do something like this? How can I basically get xi of t, which is expectation of n squared of t? What can we do? So one thing that I am highlighting for the second time, which is there is always in your bag of tricks, there is always this trick of conditioning on the first arrival. Very useful and very powerful, in which like you take an expectation, you take something, and then you say, okay, let's condition on the time of the first arrival. And so basically what you do is I treated expectations, and you say, well, I have this expectation that basically the conditional version is given that the first arrival occurred at time alpha, okay, and then you multiply by fu of alpha, the alpha, and then you integrate from 0 to infinity. Okay, now what if alpha is greater than t? If alpha is, so this is the time of the first arrival. If alpha is greater than t, so that the first arrival in the system, it occurred after t, then what is the number of arrivals at time t, which is less than alpha, which is the time of the first arrival? So this is equal to 0. This is equal to 0. And so basically our integration here is effectively from 0 to t. Expectation n squared of t given u1 is equal to alpha fu of alpha d alpha. Okay, so so this is again because n of t is equal to 0 if the first arrival occurred at a time after t. So if you inspect the system at time t, no arrivals whatsoever, and so n of t is equal to 0, and you know, and then here the integrand, it has n squared of t, so this guy will be 0 whenever alpha is greater than t, and so you can just do the integration from 0 to t. And then there is the other thing, which is now you know, so you have your first arrival occurs here at u1 is equal to alpha. Okay, and so what you can say is that you take this n of t, so you take n of t is equal to 1. So what is this one? It's the first arrival. It's the first arrival. So just count the first arrival plus. Once the first arrival takes place, it's as if you are resetting the system. It's as if you are restarting anew. And why is this justified? It's because the inter-arrivals in a renewal process, they are independent. Okay, so the next inter-arrival time has no relation whatsoever with what has happened in the past. And so basically, if you are counting the number of arrivals at t, well, the n of t is equal to 1. Here you are conditioning on the time of the first arrival, and you are saying that the first arrival is at alpha. So n of t is actually equal to 1 plus the number of arrivals, the extra arrivals that you get from over this interval from t minus alpha. Extremely important. And basically, this is what I did here. So n squared, but n of t itself is equal to this guy, and then we have the square. So again, very useful tricks when you deal with renewal processes. And I think in one homework problem, you can actually basically sometimes you condition on the residual time. Okay, it depends, you know, but most problems basically you know, if it's always something to try. You know what if I condition on the time of the first arrival? Okay, sometimes and you will note from the context of the problem that sometimes perhaps it's actually better like to condition on the residual time, which is that like the time from t to the next arrival. Okay, so this conditioning game, it's iterated expectations, so useful. Like it's something that is like so useful in, you know, in so many basically topics in probability and random processes. So you take the square and then you divide. You basically extend this into basically 3 terms, and now let's see. So let's here. So we have expectation. So if 5t is the second moment. Okay, this one, and now we can write it as 3 terms. So one of them is this guy, okay, which is the CDF, and one of them is the convolution between M of t and the PDF of inter-arrival. Okay, and then you will have this guy. What is this one? Expectations n squared t minus u. Here I'm using u as the, I explained it using alpha, but here I'm using as a dummy variable of integration u. What is this guy? It's just, the integral is psi of, basically of t minus u, is the integral of expectation of, okay, let's, so sorry, psi of t minus u is the expectation of n squared t minus u. Okay, and now it is multiplied by this one, so there is a convolution. There is a convolution between psi of t and so we have an integral equation, and it's like the same form above. See, so you have psi of t is equal to, let me copy it. So fu of t plus 2 m of t converted with fu of t. So this is known plus the convolution between psi of t itself and fu of t. So that's the general integral equation that we have above. Okay, and of course you do not need like to reinvent the wheel, right? So basically, you know, you do not have like to take the Laplace transform again or anything. Just go for the solution. You know, just go for the solution. So the solution tells you that psi of t is basically the known function. It's the known function plus the convolution of the known function and basically the first derivative of the renewal function. Okay, and then we have basically we know some results. Sometimes basically we prefer to write down things or to be everything in terms of the renewal function. Rather than like having the PDF and the CDF and the renewal function. Perhaps sometimes it's useful to write everything in terms of the renewal function. So here we have like everything does not look like nice. So we can basically use ideas like M of t. Remember those guys. M of t is equal to fu of t plus fu of t convolved with M of t. And it is also equal to fu of t plus fu of t convolved with the first derivative. So those are your friends. You can use them. So for example, here you have basically M of t convolved with the PDF. So according to this first relation, M of t convolved with the PDF is actually the difference between M of t and the CDF. So this one, I can use it here. And then here we have f of u convolved with the first derivative of the renewal function. And according to this second one, the CDF convolved with the first derivative gives you the difference M of t minus the CDF. So this is basically this term here. And then this one, M of t convolved with the PDF, is M of t minus the PDF. So basically you can apply these two formulas to basically get rid of these convolutions. You are still left with one convolution here. Then you start to basically collecting the terms. 2m of t and m of t, that's 3m of t. You have big F minus 2 big F minus big F. Okay, so I have minus 2, and then you have 2m of t convolved with the first derivative, and then you have basically minus 2 f of u. I think I perhaps did yeah, okay, I did like a step, it's not clear. So this minus 2, okay, so there is a minus 2 from here, minus 2 fu of t convolved with the first derivative. Again, it's nothing but this guy here. So this is minus 2 m of t minus fu of t. Okay, so now the very nice thing is that here you have minus 2 and minus, so that's plus 2 with minus 2. So you can say bye to the CDF, and you have now everything expressed in terms of the renewal function. Basically, epsilon of t is this thing, and you can actually check it. Check that you get what you expect, like in the Poisson process. Okay, so the general renewal equation is again something that and of course, like once you get an equation, an integral equation of this general form here, just use the result directly. You do not need to redrive basically what is going on. You don't need to like take the Laplace transform and then do the tricks that we did above. And again, keep those guys in mind. Again, because sometimes I think like perhaps in one problem or something, I will tell you explicitly that I do not want to see small f or big F. I want everything to be expressed in terms of the renewal function. And the reason for this is that sometimes you basically spend time to get the m of t, and then like you want everything to be expressed in terms of the renewal function. Okay, any questions? Okay. So we are done now with the renewal processes, and so let's go to discrete-time Markov chains. So discrete time. So we are talking here about special case. So we are talking about Markov processes. So this is a Markov process. So you say that the Markov process is discrete time. So with a discrete index, right? So discrete index, right? So we know what is a random process. A random process is an indexed collection of random variables. That's basically the random process. The random process is an indexed collection of random variables, right? So the index can be anything. The index can belong to anything, and so it can belong to it can be a real number. It can be a non-negative real number. It can be an integer. It can be a non-negative integer. It can be a positive integer. All those are valid, basically, index sets. Okay, so we talk about discrete time. So discrete time here refer that we are talking about a random process whose index is, specifically in our case here, it will be a non-negative integer. a non-negative integer. Okay, so recall that again, a random process RB. So basically, this is an indexed collection of random variables, and the index, index can belong to a finite, countably infinite, or uncountably infinite index set. Okay, and like renewal process is n of t, and we took t to be a non-negative real number, right? N of t. Now we will talk about x sub n. So the index here is a non-negative integer, and so the Markov process is now so this is like special Markov chain. So it's a Markov chain if the random variables. So the index of the process is discrete, specifically a non-negative integer, and it's Markov chain. The random variables of the random process are discrete random variables. The random variables are discrete, which means that they take values from either a finite set, so almost surely, with probability 1, they take values from a finite set or from a countably infinite set, but not from an uncountably infinite set. Okay, so there is the index, and then if you fix the index of the random process, then you get a random variable. So when we say Markov chain, then the random variable we are talking about is a discrete random variable, which can, with probability 1, it can assume either a finite number of values or a countably infinite number of values. And the index is basically a non-negative integer. Okay, so that's basically the business of discrete time and Markov chain. But what about Markov process to begin with? What is a Markov process? So basically, the idea is for a Markov process is that the future and the past are conditionally independent given the present. And of course, this is, it needs to be written like in a mathematically rigorous way, and basically the remaining part of the lecture will be what is exactly the Markov property. Okay, but like you can say it like this in words, that a random process is a Markov process if the future of the, so you fix some time, and this is like the present, and if the future and past are independent, not independent, they are conditionally typically they will be dependent, but for the process to be Markov, they need to be conditionally independent given the present. Okay, so again, so DTMC, to make sure that we know what we are talking about. DT, so index is a non-negative integer. Okay, so we'll talk about guys x of n, and n basically belongs to the set 0, 1, 2, 3, and so on. Okay, and then Markov chain, so random variables are discrete. Okay, and then Markov itself means that past and future are conditionally independent given the present. And it is this statement that we need to sort of make it rigorous mathematically. It must be something that that everyone agrees on, and it can be used to derive mathematical results and so forth. Okay, so this is the business. And continuous time Markov chains, basically the idea is that you will change this discrete time into continuous time. So you will make the index a non-negative real number. Okay, so the difference will be playing in the index. But it will be also Markov chain in the sense that the random variables are discrete random variables, and Markov, which means that you have the Markovian property. Okay, here is the Markovian property. Okay, so I will just write it down in a certain form, and then we will show that this certain form implies many things. Okay, implies many things that you can later use directly. Okay, but this is like the main definition. Okay, so our random process has the Markov property. Okay, now if for every n equals 1, 2, and so on, the probability of x of n taking a certain value given x of n minus 1, x of n minus 2, x of n minus 3 up to x of 0, the indexing here starts from 0, that this probability is the probability of x of n just given this guy only. So see, what happens now is that x of n, so you can like in words say that given x of n minus 1, given x of n minus 1, this is not generally a true statement. It's a statement if we condition of x of n minus 1, x of n is independent of x of n minus 2, x of n minus 3, all the way to x of 0. This is basically what this means. And that's the Markov property. That's this business of basically, so like n is like the present. Sorry, n minus, here in this definition, it's like n minus 1 is the present, and n is the future, and n minus 2, 0 to n minus 2 is the past. So the future and the past are conditionally independent given the present. Okay. Now, starting from this, again, let's basically derive results that will be very, because the Markov property will appear in various forms. And we do not need, like, we do not, sorry, it's not like we do not need, we do not want, basically, like, to do everything from scratch. Like, every time you want to do something, you want to start from this one. So, okay, so this one implies many basically, it has different forms. All of them are useful, and we can just use them directly once we basically understand why they are true. Okay, so let's take this one and reproduce several other useful forms. Okay, let's take the joint distribution of those guys. The joint distribution of x0, x1, x2 up to xn. Okay, for the chain rule. So there is a chain rule, and this is applicable for any joint distribution. Okay, so you can take a probability of x0, x1, x2 up to xn, and then you can write it like this. It is probability x0, x1 given x0, x2 given x1 and x0, x3 given x2, x1 and x0, x4 given x3, x2, x1 and x0, and so on and so forth. Okay, so this is general. Okay, so this is general, so long as, so this is general, so long as the conditional distributions are defined. Okay. Now, what if we have this Markov property according to this definition in red? Okay, this guy remains as is. This guy remains as is. Not interesting. But what about this guy? x2 given x1 and x0. So according to this definition, we can just stop at x1. We can eliminate the x0. What about this one? You have x2, x1, x0. You can eliminate x0, you can eliminate x1, and you can stop at x2. What about this one? You can eliminate everything and you stop at xn minus 1. So this second line now, this is a specific for Markov processes. So for Markov processes, the chain rule becomes this very nice thing that you need like to know by heart. That this probability x of n can, for a Markov process, can be written as bx of 0, bx of 1 given x of 0, bx of 2 given x of 1, bx of 3 given x of 2, and so forth. Now, if you don't have the Markov property, then basically what the set that the guys they are conditioning on, they keep increasing and increasing. But if you have a Markov property, basically, according to this definition above, you can just have, a conditional distribution just involving one random value. Okay, so this is very nice. And we can write down this in another form. Again, it depends. Sometimes this is useful. Sometimes the other form is useful. So basically, go to this guy. Now, what we do is combine these two guys together. Okay, so this is b of x0. B of x1 given x0. Okay. Now, rewrite it as joint between x0 and x1. Okay, we can do that. And then the joint can be written in another form. I can take b of x0 and x1, and I can write it as, rather than here b of x0, b of x1 given x0, I can write this as b of x0 given x1, b of x1. And then you can take this b of x1 and take it with b of x2 given x1, and then rewrite this as b of x1 given x2 multiplied by b of x2. And keep doing this till you get this guy here. So now it is b of x0 given x1, b of x1 given x2, b of x2 given x3, and you have all the way up to xn. So we have another form that is very useful. So in this one, you start by b of x0 alone, and then x1 given x0, x2 given x1, x3 given x2, all the way to xn given xn minus 1. But sometimes it is useful to write it like b of x0 given x1, b of x1 given x2, b of x2 given x3. You go all the way to b of xn minus 1 given xn, and then you finish it by b of xn. Remember that basically to write down something like this in which we are conditioning on just one random variable, it's thanks to the Markov property. Otherwise, we need to do this, use this monster here. Okay. Now, what if basically our conditioning is not all the way to x of 0? What if we stop somewhere in the middle? Are we justified in applying this rule again? So suppose that you have basically something like this. So here it is, b of xn equal to some specific value in, and typically in this part of the course, S will be the set of all possible states. And so yeah, what is this business of states? Okay, so let's actually define it. States, the values taken by the discrete random variables constituting our random process are called states. See, again, if you fix the time index, if you fix n, then you have a random variable. And what random variable? Since we have a Markov chain, then the random variable is simply a discrete random variable. It takes values from a finite or countably infinite set. So this set is called S. And those values, in the context of Markov chains, they are typically referred to as states. Okay, so they are just the values that the random, that basically the discrete random variables take. Now, so suppose that you have the probability of xn given xn minus 1, xn minus 2, xn minus 3, but you stop at xn minus m. Perhaps you do not obey the main definition, and you do not go all the way to x of 0. So what will happen if you stop at xn minus m? Good news. The good news is that actually what we have is also equal to this one, in which we just condition of xn minus 1, but let's just show it. So to show it, we need basically the results so far, okay, and the law of total probability. It's the always friend. Okay, so here is the story. Take this conditional probability and use base. Okay, so I can write down this conditional probability joint. So xn is equal to in, and then the other guys here. Okay, and then in the denominator we will have the probabilities of those guys. Okay, so base. Probability of x, basically, or of omega given gamma is probability of omega and gamma divided by the probability of gamma. Okay. Then apply the law of total probability. So the law of total probability. So you have this distribution here. It involves x of n minus 1. It stops at x of n minus m, right? So here is what you can do. You can basically continue. You can have x of n minus 1, x of n minus m minus 1, x of n minus m minus 2, all the way to x of 0. And then you have a summation in which you sum over all the possible values of those random variables. Okay? So, like, if you have, if I give you a problem in which you have this summation here, and this summation for every one of those random variables, basically it's over all its possible values, then basically the remaining, if you do the summation, you are left with basically the joint probability of the other guys, right? Remember that basically if you have, if you have the probability of random variables, let's say y1, y2, y3, and then you sum over all possible values of y3. Then you get what? You get, this is the so-called marginalization, right? You get the marginal of y1 and y2. So you start with the big thing, and you are interested just in the first two guys. You simply sum over all possible values of the third guy. And we're doing summation again, not an integral, because our guys here, by definition, Markov chain means that our random variables are discrete. And so they take, again, values from a finite set or a countably infinite set, which I refer to as big S. Okay, so this is basically the idea here. So this is like basic probability. So you go here, you apply Bayes, and then you say, okay, the original definition of the Markov property, it has basically all the x's all the way to x of 0. And so you continue, but here you stop at x of n minus m. So you say, okay, I cannot just continue. I need to continue up to x of 0, and then to have the sum over all possible values of x of n minus m minus 1, x of n minus m minus 2, x of n minus m minus 3, and in the denominator we will do the same trick, which is go and continue up to x of 0, and then basically do a summation. Okay, then what? Then apply this chain. Now remember that basically if you have the Markov property, you can, this is very important, you can take a joint probability and like b of x0, x1, x2, and so on, you can write it like this. I can write down this probability here in the numerator as b of x0, b of x1 given x0, b of x2 given x1, b of x3 given x2, and then b of xn minus m given xn minus m minus 1, b of xn minus m plus 1 given x of nm, and so on. So you can basically do this, and you can do this in the numerator and denominator, again, because you are assuming that you are talking about a Markov process, specifically a discrete-time Markov chain. And then you compare the numerator and denominator, and they are exactly the same. There is just one extra term that is in the numerator, which is this guy here. Okay? And so this one is equal to the probability of xn equals in, given xn minus 1 equals in minus 1, xn minus 2 is equal to in minus 2. The idea is that you stop at x of n minus m equals in minus m. So it doesn't matter. So if you do not go all the way to x of 0, well, I mean, you can just stop at x of n minus 1. So this means that we have actually a family of equalities. So you go all the way to x of 0, or you stop at x of n minus 3, or at x of n minus 2, and so on. You still get that all those guys are simply equal to the probability of x of n given x of n minus 1. So actually, despite the fact that this is the formal definition of the Markov property, perhaps it is actually, it means this thing that people say, that the future and past are conditionally independent given the present. So let's basically try to do like a general proof. Again, so that we get a result that will allow us to use the Markov property in many of its various forms, right? Because we do not want everything to start from this one here. This would be like so boring and annoying. Okay, so let's actually do the so-called extended Markov property, which again is like sort of generalization of the Markov property that will allow us to play like more sophisticated games. And so here what I will do is this. I will take an event F. I will take an event F, okay? And this event F is basically, okay, so F is an event that depends on x of n plus 1, x of n plus 2 to x of n plus n, or n is some number, some finite number, positive number. And then there is H, which is defined in terms of x of 0, x of 1, up to x of n minus 1. And then there is x of n, and then there is x of n itself. Okay, so our guys now are basically those. So we have x of n, x of 0, x of 1, up to x of n minus 1. So H depends on these, or H depends on these. Or you can say that H is an event in terms of these. It's like the best. X of n is like the present. And then basically we have x of n plus 1, x of n plus 2, up to x of n plus n, and basically n, okay, and those are basically, so F is the future. It's an event in terms of these. Okay? An event in terms of this. Okay, so the idea is that, okay, so what is basically the idea? We want again like to be more general and not every time to go back to the very original definition of a Markov property. We want to show, so basically desired is that the probability of F given x of n is equal to I and H, okay, that this is actually probability of F given x of n is equal to I. So that's the desired thing. So future F and H are independent given x of n. Okay, so here basically the idea is that F and H are conditionally, they are not independent, you know, they are conditionally independent given x of n is equal to I. Okay, how can we show something like this? So let's basically start with this right hand side. Okay, so let's like put it in a form, and so the idea is like, you know, we will take this guy and reach a certain form. We will take this guy and reach the exact same form, meaning that basically these two are the same. That's the idea. And what are our tools? Our tools are basically what we have so far. Law of total, also using law of total probability base, stuff that is not more complicated than this. Okay, so probability of F given that x of n is equal to I base, so it is the probability of F comma x of n is equal to I over the probability that xn is equal to I. Okay, and then you want the law of total probability. So the law of total probability, basically in the numerator, F is an event in terms of those random variables. So basically you will have the joint distribution, So x of n equals I, it's here, and then those basically are basically the random variables, the future, x of n plus 1, x of n plus 2, up to x of n plus small m, and then you have a summation, you have summations that basically depend on how F is defined. So those sums, you know, we want the probability of F, comma, x of n is equal to I. Okay, and so what is F? It's defined in terms of x of n plus 1 up to x of n plus 1. So we will have sums with indices in plus 1, in plus 2, up to in plus m, and those indices, you know, it's not that each index will go over the set S which includes all possible values, those discrete random variables can take. Those sums will be defined based on how actually the event f is defined. Let's give you an example. Suppose that f is something that looks like this. Suppose that suppose that we are interested in the probability of x of n plus 1 less than x of n plus 2, comma, x of n is equal to r. So here I'm not saying that f is one of those guys or anything. F is an event that depends on those guys, and it can be like one of those like events that that appears a lot in our work, like this one. So perhaps f is this probability is the event that xn plus 2 is greater than x of n plus 1. Okay, it can be that x of n plus 1 is equal to 7. In that case, the summation of x of the summation over the index I plus 1 will just have one term, because you are fixing it, right? So in this case, to be concrete, suppose that every discrete random variable in our discrete-time Markov chain can take any one of those 4 values, 1 or 2 or 3 or 4. Then what is our sum here? If f is actually this event that x of n plus 2 is strictly greater than x of n plus 1, well, we will have a double sum because we have 2 guys here, and basically one index which is related to x of n plus 1, it will go from 1 to 3. It will go from 1 to 3, and the other index related to x of n plus 2 will be index I n plus 1 plus 1, because x of n plus 2 is strictly greater than x of n plus 1. So if x of n plus 1 is 1, then this guy can be 2 or 3 or 4. If this guy is 2, then this can be 3 or 4. If this guy is 3, then this can be 4. If this is 4, well, we cannot have any value for this guy. So basically, I n plus 1 will go from 1 to 3, but I n plus 2 will go from I n plus 1 plus 1 up to 4. And then you put here probability that x of n is equal to I, probability that x of n plus 1 is equal to I n plus 1, and the probability that x of n plus 2 is equal to I n plus 2, right? And now this event, if you look at those guys and you look to the summation, the indices of the sum and how they change, this one is from 1 to 3, the other one is from I n plus 1 to 4, then basically what is the event? So suppose that I do things in reverse. I give you this thing and I tell you what is event f. You look here, so basically event f, event f is that basically this guy is strictly greater than this guy, because for I n plus 1 it takes the values from 1 up to 3, so it takes every possible value except the largest, and then xn plus 2 it takes all possible values that are greater than x of n plus 1. So basically this will be the event. So the sums here are basically sums that depend on give me my f, how the event f is defined in terms of those guys, and I will tell you basically what each sum, what the limits of each sum look like. Okay, so so basically you take f of n given x of n equals I. Again, you apply base, then you focus on the numerator, and when you focus on the numerator, you write it with the sums, and then you use our friend, which should always be in your mind. So basically, if you have guys like this, and you have a Markov chain, then you can take 1 and then BA2 given A1, BA3 given A2, and so on, proved on the previous slide. Okay, and so basically you can take this joint monster here and you can write it as, like those guys, this, and then this conditioned on this conditioned on this, and so on and so forth. Okay, here I actually did it in 2 steps. Okay, but actually, given that your process is Markov, then you can actually write this line directly. But here is a reminder that the first line is always valid, so long as the conditional probabilities are meaningful. But then, because of the Markov property, you can just take each guy and condition it on the previous pal. Okay. Now, this guy, there is nothing in the, this guy's probability x of n is equal to I, and, basically the things that are changing here are those indices I n plus 1. This guys actually can be pulled outside, and it can eliminate whatever we have in the denominator. And so actually this probability of f, which is an event in terms of x of n plus 1, x of n plus 2, up to x of n plus m, this conditional probability is given by this summation. So the trick now is to restart, but now conditioning on x of n equals I and h. Now h is an event in terms of the random variables x of 0, x of 1, up to x of n minus 1. It's like the best. And we will basically, if we can show that this conditional probability is also given by this summation here, then this guy is exactly equal to the probability of f given x of n is equal to I, and hence f and h are conditionally independent given that xn is equal to I. Okay, so let's basically try to do this. The procedure now is like sort of, an addition. So you take this thing, and then you use base, and then you basically take this one here, and you write it in terms of sums. Now in the denominator, basically we have h, and in the numerator we have h and f. So in the denominator, again, we will have basically those guys, and we will have those summation indices. And what are their values? They depend on how h is defined. Okay, so suppose that as an example that h, h is basically that x of n minus 1 is equal to 7, okay, and x of n minus 3 is basically equal to, let's put it greater than or equal to 5, okay, and let's suppose that s is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so to make sure that we understand what we are doing, so what will be this summation? Okay, so our best now, it depends on those guys. Okay, so I have summation in minus 1, summation in minus 2, summation at minus 3, summation in minus 4, all the way to I of 0. And the challenge now is, and then we have the probability that, x of n is equal to I, and then x of n minus 1 is I minus n minus 1, all the way to x of 0 is equal to I of 0. The challenge now is what are basically the limits of those sums? Let's see. So, h basically is defined in terms. So basically, the other guys that are not here, they can take any possible value, right? So n minus 2 is not here. So basically, this will be from 1 to 10. This will be from 1 to 10. This will be from 1 to 10. Okay. What about x of n minus 1? It must be equal to 7. So basically here, this summation here will just be in minus 1 equal to 7. It will be just one term. And then x of n minus 3 should be greater than or equal to 5. Then this guy will be from 5 to 10. From 5 to 10. Okay? So again, those indices here are, the summation indices take values according to how f and h are defined. Okay, and you can take an event, and it can be complicated event. So basically here, like everyone is like, this takes a value, this takes like a range of values, but like I did also an example in which like one of the random variables is less than or equal to the other. So the events can be as complicated as you wish. As complicated as you wish. It's not just that you need like each random variable taking a certain range. Okay, so keep this in mind. We are trying to do like a very general proof, so that later, you can apply the rule for any f or for any h. Okay. So so let's go here now. Apply the Markov property. So for each one of those joined guys, you start with, okay, x of 0, x of 1 given x of 0, x of 2 given x of 1, x of 3 given x of 2, and you go, or there will be x of n plus 1 given x of n, which is equal to I. We are conditioning on this one. We are fixing x of n as I, and then you go all the way to x of n plus m, because we assume that the future event depends on the random variables x of n plus 1, x of n plus 2, up to x of n plus m. Do the same thing in the denominator, but like in the denominator, we just stop at x of n, and then compare. You will find basically that this thing in the denominator, which is this one here, it's like this thing. It's like this thing. Okay, I am overshooting. So it's like this thing, right? And the other guys, they don't depend on those indices, I0, I1, Okay, so, those will go with those. Okay, so those will go with those in the denominator. So basically, it's like this term, it's basically, it has like an equivalent, an equal term in the denominator, and we are left with this. Okay, and this is exactly what we obtained previously, which is this one. Okay, so so now we have basically that our required result. So let me show you that situations in which you can directly use this result. You do not need to reinvent the wheel or go back to the main definition of the basically the Markov property. So probability x of n plus 1 is k, given xn is I, and xn minus 1 is j. Okay, so n plus 1 and n minus 1, we can actually remove this guy here. Okay, that's that's sort of straightforward. What about this one? N plus 1 and xn minus 1, xn minus 2. So there is an event here that depends on xn minus 1. Okay, it's a bit more complicated event. It's not that x of n minus 1 is equal to something and x of n minus 2 is equal to something. No problem, because actually our proof will work for these things. Okay, so we can eliminate this one. What about x of n plus 7? So that's the future. X of n is equal to I, x of n minus 3. Go away. X of r, x of s, x of q. R is greater than s, and s is greater than q. So this is like sort of the present. So like this is the present. Okay, and you can just eliminate this one, right? You can also show, I will leave it to you. You can also show that basically, this one is also true. So what if you take the conditional? What if you take the conditional b of h given xn is equal to r? Sorry, x of n is equal to I and f. What if you condition on the future? Okay. Well, you can show, and you are highly encouraged to actually go through the derivation and to do it yourself and convince yourself that this is true. This is the probability that h is given x of n equals 1. Right? So, so something like this. See, this is different from the main definition of Markov. This is x of n given x of n plus 1, x of n plus 2, x of n plus 3, up to x of n plus m. So here we are conditioning on the guys that will come in the future. Guess what? The Markov property also works in that direction, and you can simply eliminate those, and you write this as x of n given x of n plus 1. Very important, right? So if I write, you have probability that x of n minus 1 given x of n and x of n plus 7. Well, this is probability of x of n minus 1 given x of n. You can just eliminate this one. Okay. And let's choose n greater than r greater than s. So what is the joint probability of these two guys? So again, from the chain rule, basically this is x of, you can write this as x of n given x of r multiplied by the probability of x of s x of s given x of n and x of r. But now if this is a Markov chain, here we have x of s, and here is s, index s. Here we have x of r, which is like the present, this is the past, and this is the future. By the Markov property, you can eliminate this one, and now b of xn given x of r is equal to b of xs given xr, which means that if you have your time is like this, x less than r less than n, then x of n and x of s. So basically the random variable with this index and that index are conditionally independent given x of r. Tell me what x of r, then these two guys becomes conditionally independent. So the extended Markov property is very useful, again, because once you spend time to understand basically this page, because it will allow us basically to apply the Markov property like in all its forms without like having to do things